At last, we're going to reach our end goal of quantum mechanics and go on to NMR. So this has been the aim all along. We've been talking about quantum states and why things are quantized, and then we got onto angular momentum and then spin. That's aiming to get us to NMR. So in order to do NMR, we're going to talk about spin and energy. We've talked a bit about spin in the last lecture. The whole lecture course so far has really been about energy and how we calculate it. So we can look at NMR as energy levels, and that's not the only model that we can use, but I've decided to cut out mentions of the other stuff from this course because it's not really necessary to talk about. And then we're going to look at how that leads to spectra. So if you're familiar with most spectroscopy, this should be fairly straightforward. It may even be a little bit of revision for you. So let's recap. We've got two spin states. We've got one that we call up and one that we call down. Now, how do we work out the energy of those states, or the energy associated with them? Well, like everything in quantum mechanics, we have to operate on them. So we apply these operators, and these are known as the Pauli matrices. And they're a fairly simple thing, but you can wrap your head around matrix multiplication. Again, doing that soon. And the result of that should be like any other eigenfunction equation or eigenvector equation or eigenvalue equation. It should pop out the exact same wave function again, multiplied by a value. And if we do that with the Pauli matrices, we get plus and minus 1. Nicely quantized. Not quite the 1/2 we're expecting from previous discussions, but they're there. We've got one that's plus 1 and minus 1, and those are the only two states. So we've got one that's spin up, one that's spin down, two distinct energy levels. So far, so good. But we'll embed the Pauli matrix inside an operator that actually gets us proper energy. We call that a spin operator. We can calculate the spin energy using that, and we actually get a half, or Planck's constant over 2 at least, which is, if we take it in natural units, which we've done before, we get plus 1/2 and a minus 1/2, exactly as we expect previously. So that gives us two energy levels. We've got a spin up down there and a spin down as well. And the energy difference between them, if you've got plus 1/2 and a minus 1/2, will be 1, or equals to Planck's constant. Not quite, though. Let's have a look at a problem with that equation, and this is why I tell you to check your units. It's not for the good of my health, because if you look at energy, that should be in joules. Planck's constant is in joule seconds. Not good. That's a unit mismatch. It doesn't work. So we have to do something to Planck's constant, and maybe if you paid attention to some of those energy levels in vibrational spectroscopy, you can see where this is going. We need to multiply it by a frequency. We need something in per seconds to cancel out those seconds. So if we stick a frequency in there, suddenly we've got an equation that works. There must be some kind of frequency involved. And in magnetic resonance, that frequency comes from the gyromagnetic ratio and the strength of the magnetic field. So this is telling us that when the magnetic field is 0, so if B is equal to 0, then the energy difference is 0. So in the absence of a magnetic field, those spin states will be degenerate. This is why basically spin up and spin down around a hydrogen atom for an electron are effectively identical. There is not a sufficiently strong enough magnetic field to split them. But if you put a hydrogen atom into a magnetic field, you do get a sudden split. It's called the Zeeman effect, and it means you get line splitting in your spectra. So if you pass a hydrogen through a magnetic field, which you can do in sunspots, they're really highly powerful magnetic storms on the surface of the sun, you see your spectra of your hydrogen atom suddenly split into multiple lines. That's the spin states no longer being degenerate. But how does that help us with NMR? Let's switch to some NMR terminology as well. So we're going to stop calling them spin up and spin down and refer to them as alpha and beta. Spectroscopists sometimes use spin up and spin down as well, but really we're interested in calling them alpha and beta out of the NMR tradition. That's not the only thing that changes. That diagram flips upside down, the alpha state, spin up, is on the bottom, the beta state, spin down, is on the top. That's not just a nomenclature change, there's actually some physics that flip that upside down for the proton. There are other NMR active nuclei where it flips back again, and the alpha state's the higher energy one and the beta state's the lower energy one. Spectroscopic physics, gotta love it. But the energy difference there is proportional to the magnetic field. And that means we've got two energy levels. This can work like any other form of spectroscopy. If we've got something in a higher state, it can drop down to a lower energy state and release energy. Or we can put energy in and it promotes it to a higher energy state. So we've got absorption and emission spectroscopy happening. NMR is a little bit different if we put in another model for how that works, but I'll probably discuss that in a supplemental video rather than this main series. So we can add in energy and promote these protons up and down between the two spin states. And the range of that energy is in radio waves. Previously in spectroscopy, we've covered UV, infrared, microwaves, and then radio waves. Yes, that's the right way around. So radio waves we finally got onto with NMR. So there's spectroscopy all across the electromagnetic spectrum. It's really low energy. So how does this form into a bit of spectroscopy? Well, the nucleus of an atom has that spin state. They're being cheeky and treating it as a bar magnet there. And it has electrons around it. And electrons themselves are spins that have a magnetic field attached. So they either work with or against the magnetic field that we apply. So that big NMR cryostat that you see, they cost millions of pounds and it's fueled by liquid hydrogen, liquid helium and liquid nitrogen. That's generating a field, but that's not the field that the proton actually experiences. It's manipulated by the electrons around it. And we call that chemical shift, or the electrons around it are the chemical environments, and how we shift the field is the chemical shift. So that is then now a portion of the applied field. So we call that B0, we call it the applied field. Now, we can't necessarily expose a proton to just that. So what we do is we just reference it to a compound, in which case it's tetramethylsilane or TMS, and we just define whatever the protons on that are doing as delta equals 0. You've probably come across that in previous lectures on NMR. We're just putting it in there to recap it. So as things get more shielded, delta increases. As they get de-shielded, delta changes as well. So that means that splitting there can change quite a bit. If we have a high chemical shift, it will increase, and if we've got a low chemical shift, it will decrease. So we have 3 protons, maybe they're in 3 completely different chemical environments. So we've got 3 different possible energies for these transitions, 1, 2, and 3 of them. And what we can see is that will produce 3 peaks on an NMR spectrum. One level will appear here on the spectrum, and another level will appear here and there. There are a few added complications to that, especially when they start interacting with each other, but this is the general outline. If we've got a different chemical environment, it is manipulating the magnetic field that the proton experiences. It manipulates the energy levels between these transitions, and so it manipulates the amount of energy we need to make a transition, going from the spin up to spin down, vice versa. That transition will require a different energy. So that's the basis of NMR. So spin states aren't degenerate in the presence of a magnetic field. The stronger the field, the bigger that energy gap between them. And that means we can do spectroscopy. And it's particularly we can do chemical spectroscopy because that field is influenced by electrons and the chemical environment. So it means if we fire radio waves at something in a magnetic field, we can actually get different absorptions depending on where a proton is in a molecule.